Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program. So, as some of you have seen before, I have been conducting this what I call system conversations with our prestigious speakers that we bring to Cornell to share their views, their research with us about anything related to systems. So today, I'm really delighted and honored to introduce to you Dr. Andrea Serrani, and he received his PhD degree in artificial intelligence and also systems from the University of Ancona back in Italy in 1997. And actually, it turns out that that degree was not enough. So, so he moved on. Actually, he got his Doctor of Science degree in System Science and Mathematics from Washington University in St. Louis back in 2000. Since 2002, he has been on the faculty with the Department of Electrical and Computer Engineering at the Ohio State University in Columbus, Ohio, where he's currently the professor as well as serving as the associate chair for the department. I just want to mention very briefly his research. His research activity spans the fields of control and system theory, with emphasis on nonlinear and adaptive control, tracking and regulation, and application to very exciting areas, including aerospace and autonomous systems. So, Dr. Serrani, as you see, I was talking about your background. I believe myself and also I believe our audience is we are so impressed with all these different background and experience, and I believe we would love to learn more about whatever you want to tell us.
Well, thank you, Oliver. First of all, let me tell you, this is a great privilege for me to be here. This is my first time at Cornell, and it's been
Welcome,
wonderful.
Cornell.
Very, very happy to be here and having this conversation with you, and I'm looking forward to the interaction with all your faculty and students, which I already had this morning, a snapshot of it, which was very, very engaging. So thank you very much. So yes, I mean, my trajectory has been interesting in a sense because I studied in Italy, working in my home institution and doing a PhD that focused on underwater robotics. And at that time, that was very exciting, but I felt somewhat the need to go more in depth as far as the theoretical aspects of the discipline were concerned. And the opportunity came at the time with a Fulbright scholarship. And then I went to Washington University for a year, and then I continued my study there. And I was lucky enough to be part of that. At that time, was a very outstanding group in nonlinear control and system theory. So I was able to, for 4 years, to dedicate my study to theoretical foundation. So I took math courses and courses in dynamics and nonlinear control and systems. And then when I went to Ohio State, I realized that it was time to apply this type of expertise and knowledge to problems that were of interest to several agencies. And in particular, at the time when I moved to Ohio State in 2002, I was very lucky because they had already very recently established a collaborative center of excellence with the Air Force, in the Air Force Research Lab, which is located in Dayton, just about an hour drive from Columbus. And that proximity made it possible for me to interact with researchers at the Air Force Research Lab. And that's where I started working on problems of very practical nature, in a sense, but whose possibility of being successful in tackling this problem required a lot of finesse in terms of modeling, control expertise. And I started working on aerodynamic flow control, which was something that I never had imagined, and I know nothing about aerodynamics, right? And also what started to be a long collaboration on control of hypersonic vehicles, and then turned into flapping wings Microair vehicle. But what was interesting at the time is that I had no idea about the language in engineering fields other than control systems and system theory. So it was a very steep learning curve to be able, and we're talking about engineering, right? So I was collaborating with mechanical engineers, with aerodynamicists and structural engineer in aerospace. And I realized we weren't even speaking the same language. Within engineering, I mean, I'm not talking about, going and working with biologists, of course.
That's right, yeah.
So that's where I realized that we need to listen before we are able to say something meaningful in other disciplines. Well, this is in a sense the beauty and the curse of control and system theory, right? Because you are equipped with all of these tools that stems from your understanding of the dynamics in terms of the modeling, the differential equations, the mathematical property. But then you need to, step down from your ivory tower, and when you're entering fields where people have worked, for their entire life, they know what they're doing, and you need to be able to learn from them in order to contribute, because otherwise you're not relevant, and you want to be relevant, right? Because perhaps our best gift that we can give is how to optimize what people have already been doing and find ways to make that, to find new approaches, but without violating the physics of the problem. And that remains the biggest challenge. It's a challenge of culture, and
it is.
You need to be able to embrace other cultures to be successful, and that goes even in engineering.
Yeah, Andrea, I think you hit exactly the key point. It's kind of I feel when you talk about your kind of the trajectory, the evolution of your career, even though you said that you were lucky, but I really feel like you were really brave to kind of get out of your own comfort zone. Actually, as you embraced,
Wow.
Instead of especially kind of you were a kind of a theorist turned engineer.
Yeah.
Right. And
exactly.
As you said, kind of you went through like a kind of very steep learning curve.
Yes.
But that's why I think you were brave enough to take on the challenge.
Well, you're very kind. It was more of a matter of survival, really, right? So you want to thrive, right? And at a certain point, you ask yourself, which direction should I go? Which direction should I be more effective? Not just a matter of being successful, but being effective, right? So you're part.
That's right.
A big university like Ohio State, you have the possibility of collaboration with a lot of people, but you need to be able to take a few hits every once in a while, learning, and then eventually and having fun doing that. That's the best part of it, right?
Yes, that's right. It's kind of, as you say, it's kind of we have to change, like as you say, like the culture, and then of course when the culture kind of when the culture is realized in the individual, and it's translated in the individual, it's actually a mindset.
Yeah.
I think you've been kind of very, and also you have been positively, even though like you are saying it was really probably the outcome of survival.
Yeah.
However, I think it's really those at those kind of time points where like the attitude you have, whether it's being a positive attitude, proactive attitude versus a passive attitude, that I think changed the feeling you have about that experience.
Yeah, when you start, I arrived at Ohio State, very young faculty, but young faculty in terms of academic, right?
Junior, yes.
So I started sending a proposal, and proposal where in the wake of what I was doing at Washington University, and they all got rejected because. And then I started thinking, is that really what we want to do? Like continuing doing the same thing, or perhaps it's time to change the course and looking at things that I can get excited. And of course, it's going to take time before you're establishing yourself, but it paid off to a certain extent, of course, like everything. But as you said, we are lucky to be in a field and in a position where we can really go in different directions.
Yes.
Now, the older you get, the more difficult it gets, because the time you can devote to read new things is shrinking.
And you become a bigger ship, which has a bigger momentum.
Or a big inertia.
Yes.
That's a nice way of putting it, but you know how it goes, right? You get more responsibilities from other sources and other areas, but yeah, it's been fun, and the best thing in our field is the pleasure you get from collaborating with other people.
Totally agree with you. I think it's kind of your example. You are really a wonderful example, kind of, which I will come back later. Kind of for future like systems engineers.
Right.
And I think systems is actually one key feature is about being adaptive, right? And so that you can adjust to of course in your control, right? A lot of it kind of adaptive theory. So now I would like to kind of change the topic a little bit about since you started with this system science, even though you are doing this kind of engineering application, but I believe all the things you did before, all the time you spent before learning system science, even though you are not specifically doing it today, but I believe that could be a very fundamental thing that is supporting you to do the things you are doing today. So I have two questions. So from your point of view, what do you see as system science? So because honestly, I think you're probably the first speaker we brought in. I feel like at least your background was in system science. So I'm curious to learn about what your view is about system science. That's the first question. And the second question is, how do you feel your training in system science kind of is now helping your research, not only a specific research, even the views you have regarding the real world?
Yeah, those are at the same time easy and difficult questions. Okay, it's easy in a sense because frankly I know nothing else but systems, right? To me everything is system. This systemic approach to tackling a problem or even learning a new subject, it's always that has been driven my entire life in terms of approach to understanding. It is the need and the capacity of organizing your thoughts, okay? Organizing it in a way that things have an explanation or are embedded in a context that makes it easier to relate with the surrounding agents. And then it's a way of systematically arranging your knowledge on certain things, your understanding at least of things. And it's also difficult because if I look back at what we meant by system science 25 years ago, we had a broad perspective from the point of view of the math behind it, but we didn't have a clear vision of what systems can really mean when you spread it across discipline. It's only in few later years that we system scientists or control theorists became aware of the fact that there is a universe around us. We kind of imploded in our approach. And we focused more on a methodology that was starting to contrive and to be contrived and didn't really expand towards reaching out different disciplines. And I think there were areas that we traditionally had an impact, mostly aerospace, for instance, and mechanical engineering and robotics. But I think the big transition, at least for some of us, was in the 90s, late 90s, where there was a lot of interest in systems biology from that point of view. And apart from what we could actually do in systems biology, it was a change of focus and the understanding that the systems approach can be used as an umbrella to bring together and permeate other fields. And by systems approach, I mean this organization of the way you're thinking, in terms of units and their interconnections. The understanding that nothing works in a bubble, that what you do is the result and what you experience is the result of a lot of different influences. But there is a way to put some order in these influences and to prioritize and to tackle a problem by subdividing the problems into problems of increasing complexity and understanding that can be done in several different things. I mean, look at dynamics. One way of tackle complex dynamics is to take a look at the way time scale is applied to systems. I mean, systems that are faster, dynamics that are slower, that induces a decomposition. To me, the essence of system approach is decomposition.
Yeah.
Being able to not be intimidated by the sheer complexity, but finding your path by limiting yourself initially to a certain aspect and then realizing that this can be then interconnected to other units.
That's wonderful. So it's kind of, I feel like kind of, in your discussion about, system science, I feel like I pick up, several keywords. Kind of composition versus organization.
Exactly.
Right? How do you balance these two? And also kind of, explosion versus, contriving. I think it's really kind of, while for a static system, and I think we care about, the composition and organization that kind of either at the subsystem level and at the systems level. And then if you add in the time dimension, right, there is explosion stage in terms of the the system itself as well as the research community. Right. How
Absolutely.
how
Absolutely.
we do this. Yeah. So and this is wonderful. So with this, I think you mentioned earlier that we're lucky like in this kind of age where, and also I think one of the key elements that probably help you with the change or with, for example, the transition from a theorist into kind of engineering related. I think you mentioned a word, impact.
Yes.
Right. I think it's kind of wanting to have an impact, and I think kind of helps for you to migrate right from your previous field and to this field. So speaking of impact, of course now you are a full professor and you're even serving some administrative roles, and I think one key thing that academics we have is the freedom to do whatever we want, whatever we aspire. So speak of this. So what are some kind of big or small systems challenges that we humankind is facing that you aspire to apply what you have or whatever you have, in your research group? What do you aspire to achieve, and you want to impact? What kind of system challenges?
Oh, this is a difficult question because as soon as you get older, you have somehow to come to terms with the fact that you don't have the same amount of time left, and perhaps not even the same amount of resources. But there's something that I don't know if I can aspire to, but I would like to see my community tackling, and this is the issue of navigating through big data. That to me is something that we really have to come to terms with, and we have to start taking ownership of the big discussions that it's going around right now related to artificial intelligence and learning and the humongous amount of data that it surrounds us. There I see a lot of opportunities, but also potentially the seed of our destruction. We have to the temptation would be to do everything entirely driven by data and abandoning modeling principles, which have been the roots of our discipline. And because, in a sense, one of the temptations that who needs model when you can get all the information by processing an enormous amount of data fast enough. And that, to me, goes against what is the very fundamentals of the need of understanding what's going on. And to me, the biggest challenge right now that the systems community at large, and that goes from data scientists, computer engineering, computer scientists, networking,
operations researchers.
Operational research,
Yes.
Of course. I mean, optimization is now Dynamics is playing the role of Dynamics played 20 years ago.
It's an explosion, use your word.
Exactly, but optimization is everything. If you want, I mean, even in a stability analysis using the Apono function is an optimization problem, right, to a certain extent. So optimization is the common thread that keeps all these fabrics together, right? But one may argue that all of this explosion in artificial intelligence, it's really due to the fact that now we know we have availability of very powerful optimization techniques that have become more and more refined, more and more powerful. But as I was saying, we should not give up on understanding what's behind it, rather than trusting that something's going to be done because of the algorithm, right, or because of the data. And I'm very happy to see very difficult papers that I don't understand, but working on understanding what is behind learning.
The insights.
The insights, okay.
Yes.
Where does learning takes place in a deep network? It's only if we understand these things that we will be able to be successful in transitioning from like the euphoric temptation of relying on entirely on data to the more humble effort in understanding it.
And I think, thank you, Andrea. Thank you for pointing this out. I think this, of course, big data is now a hot topic, but of course, a lot of people, they even, different stakeholders, they look at big data, right, either as opportunity, as business opportunities, or, some people, seeing it as some kind of societal concerns. But I really appreciate your view. Like, you are looking at this big data challenge from this research community, right? From this research community. So, and I think you have pinpointed, several challenges. So, what do you see as our possible approaches to both, tackling this challenge as well as kind of grasping this opportunity?
I think that, as in many other areas that we collectively have ventured in, I think we have the capabilities from a methodological point of view to get a hold on to understanding this phenomenon. As usual, the challenge will be then to disseminate that knowledge in a language that's accessible to the practitioners or to theorists in other fields. As always, there is the difficult aspects of creating the theory, but then the even more challenging aspects of making that knowledge available. Because again, you may write the most beautiful theorem, but if nobody reads it, what was it for?
Yeah, you could end up with a top journal paper, but without being applied.
With 15 citations from top experts, and then what?
That's right. Yeah.
I'm not saying that these are not important. They have to be. That's where we start, or where other people start. I'm not in that category, but then knowledge is a very sterile thing if it's not applied, right? You need to grow.
Yeah. So I think speaking of this, I guess I probably would push both of us, a little bit to think about a question which, I don't know, we would feel comfortable, but I think I would like to give it a try. So one thing is that you think about this data science or this big data. In the end, as you're saying, it's a tool.
Yes.
Right. It's a tool for us to, as you mentioned, kind of the tool can be used, it can be exploited to generate knowledge, and we all know that knowledge is power. Knowledge is power. But I think from a systems perspective, I think one thing I learned from some other people, they say is that kind of engineering enables us to do things right. However, system engineering, especially even kind of the social science, we will make sure that we do the right thing. Right? It's kind of the tool used to the right thing, or it laid out, at forefront, kind of to be doing the right thing. So speaking of this, if you think about big data, the big data is it's basically immediately implies surveillance, kind of very, very broad, basically infinite, surveillance. It's essential, I think, in the future. Of course, now I'm in transportation systems. We're now talking about these autonomous driving vehicles, and in that case, each vehicle will be equipped with so many sensors, and the cars themselves will be sensors to help us monitor a lot of other things. If we're talking about a car, now we talk about individual person. We will become basically the moving sensors. So in that case, what do you see as the limit, if you think about, of course, I don't want to mention privacy, but what do you see as the ceiling or the limit or kind of the right dose of big data for us to push for this?
You're touching a very, very difficult subject, and unfortunately there is no tackling this issue without mentioning the word privacy. In a sense, this is the end of privacy, as we knew it, at least. So, if I had the answer to this question, I don't know, but it's an absolute. This is the usual dilemma, right? Where do you stop your pursuit of knowledge in the face of misuse of that knowledge? This has been the history of engineering and science wherever we started, right? In many cases, discoveries and inventions and theory have been built out of necessities that are not morally questionable, or perhaps needed at the time. Think about how much of the technology we're using today was actually developed during World War II. So, but going back to the issue of data, this is a tremendous challenge. Tremendous challenge for policymakers. Tremendous challenge for social scientists. Where do we stop? Is that a line that we need to draw? But think about the easiness in which we consciously give away our privacy. Anytime we subscribe to a social network, we click. Do we read the disclaimers? Do we read all of? We never do that. We say, I accept the terms of conditions. I accept.
That's right. Yeah, and we never know until someday it comes back to bite us.
Exactly.
Right.
So we discovered that perhaps we shouldn't have, store your credit card number on a website until the website got breached.
That's true.
So, and then we say, oh, I shouldn't have done that. Yeah, you probably should not have done that.
Yeah. I think I agree with you. It is a challenge. It's
very big one.
Looking at your research, you have been for theories turned, like control, like an expert. Of course, you can control the airplane wings,
right,
to an optimal point, where it will still satisfy the flight requirement but generate like the minimum noise, right? You can control that.
Yeah.
You can control an airplane wing. However, when it comes to social technical systems, where when humans are involved, even for you, it becomes so hard to even talk about what would be the objective function.
Exactly. And it requires a completely different set of tools, right? Because
Yes.
now you're looking at group behavior instead of individual behavior. You're talking about statistical measures. So if even thinking about stability, right? That's a completely different concept. You need to develop notions, metrics, to evaluate performance that are tailored to that type of application, which it cannot be tackled with the same type of techniques you use for a deterministic system, right? But again, it's an opportunity. And I was amazed at seeing how much linear algebra and algebraic techniques are in things like the algorithms that search engines use in determining which page to show up first in a search, right? I was thrilled to see that people in the control community, the systems community, are actually looking at these sort of things. At the end, it's an eigenvalue problem. I had no idea there was an eigenvalue problem. So the good news is that you never know your next inspiration, where it can come from. And you have to be smart in somehow thinking, okay, is this within the reach of things that I want to be involved in, or is it not? There's always a next challenge. And I agree with you that what makes us systems engineers, system science, comfortable to a certain extent is that we should have learned how to use the power of experts, right? And bringing together people from different expertise to look at a problem in a spherical way, right? If you're looking at a problem from one direction, problems of this complexity, you will never be able to make any impact whatsoever.
That's wonderful. I think this is kind of, especially toward the end of your just discussion just now. I think you made a very good point. That it is a huge challenge, but in the meantime, it's really kind of making our life very exciting. So that we don't have to just envy Newton for his age or Einstein for his age.
Right. No. And the most important thing is that you need to be able to communicate your excitement to your students. And this at the end of the day, right? We are what our students are. That is the fundamental part. Okay, we are not there to tackle problems because we work in a laboratory, right? We are fundamentally our goal is fundamentally that of training our students. So even the problems we're working on, those are at the end training grounds for our students. Our academic mission is what should be driving us completely. And if you're not excited about a problem, if you're not excited about a theory, if you're not excited about the methodology, then how can your students be excited about it? So you have to transmit, and you can get a lot of excitement from the students too. And nothing is better than seeing a student who's really enthusiastic about working on a problem and finds new problems and finds new way. I mean, that's what makes all our effort worthwhile. To see a student progressing from an initial limited knowledge on a subject to knowing much more than you do on that subject. So how many times people send us an email say, "Oh, can you tell me more about this?" Wait a minute, I need to ask my student.
That's true. Yes.
That's a good thing, right? Yeah. Because it means that you have set something in motion.
Well, this is wonderful, Andrea. You kind of transitioned us to my next question. I
Oh.
was going to ask you about education, especially I think at this stage of your career, and I really appreciate because I think early in our career, right, kind of as a junior faculty, right, you have all these 10 o'clock ticking, right,
Exactly.
working. But now I think you mentioned this very important aspect of us as educators,
Mhm.
actually, in addition to wearing the hat of being a research scientist or researcher, actually we also have a very important role
Yeah.
to be like a teacher,
Yes.
a
Absolutely.
mentor,
Absolutely.
and an advisor. So I think it's kind of, so I would like to kind of seek your opinion and also your wisdom about whatever you think as key elements or tasks for us to be educators, so that you mentioned how can we transit or pass and even train in the new generations
Mhm.
with not only the knowledge, but it's really like the excitement and
Yes.
aspiration. What are the important things we need to do, and how do we do that?
Again, difficult, but
Sorry, I just
but
posed all those difficult questions
no,
to
this
you.
is this is this is who we are. I mean, who we should be, right? We should
Mhm.
be educators first, in my opinion. And if approach to education and to interaction with your students change, and it evolves with society. Now we are much more aware of issues that perhaps 20 years ago, when I started, they were just in the background. You didn't talk about it, didn't even know about it, and being more mindful about biases, cultural biases that one may have. So that the first thing is that you need to grow as a person, as an educator, before or concurrently to how you are performing that task on your students, right? So it's you learn from your students, you learn from the environment. So it is a process that it's continuously evolving and it's dynamic. I think that one of the roles that we have as educator is, in a sense, to resist the trend, embrace the challenges, embrace the novelty,
Mhm.
but also, again, try to make order into things. For instance, one trend that I'm trying to resist in engineering is this over-reliance on the use of examples. In my opinion, we are making a disservice to our students by giving the false information that everything can be solved simply by looking at how people have done it before, right? So we are losing gradually, but very drastically, the capacity of abstraction. The capability of abstract thinking is essential even in engineering, right? We are not just people who apply things, because eventually, 20 years from now, going on in this direction, we will always be able to solve problems that have already been solved. So it's only through freeing our minds from the necessity of looking at things, at examples, that we are able to go the next step. So in my classes, I always try to emphasize this point. And in some classes, I give as little examples as I can. And this in my graduate courses, because I think students need to be challenged to think more abstractly, and without being a math class or anything of that sort. But
Well, this is really this is to me this is really dynamo, because it's really, you think about this, I think you're really hitting the essence of this education. And unfortunately, even nowadays, in people, including ourselves, you're saying you study doing this in your graduate course, but it's kind of the majority of our peers, our colleagues, we're using examples.
Yeah.
That's actually, it's a training. It's just kind of getting people to do what
Exactly.
people were able to do before. However, somehow we lose, I think, the key essence of education, which is kind of, as you mentioned, nurturing the mind.
Exactly. Open the mind.
Yes.
Think about this, okay? We always complain in systems, right, that industry could do better in doing certain things, right? So we are sometimes amazed how perhaps simplistic certain solutions may look to us, because we know that with some effort things can be done differently, but it requires you see a lot of efforts of resistance from on part of industry to change things, because part of that is driven by cost, okay, but part is also driven by mentality. So
Yes.
who are these people? These people were our students 30 years ago, right? So if you don't start setting in motion change in the minds of your students now, those are going to be the next entrepreneurs, those are going to be the next technical leaders in industry. And if you are able to open their personality, open up their attitudes towards a different way of thinking in engineering, that is not just replicating or slightly changing what has been done before, you can never get a transformative change in motion.
Yeah, that's right. So that's right. So that's actually why I feel we kind of, if you look at our society, a lot of entrepreneurs, even in kind of leaders, they were not necessarily the best student.
No, exactly.
In class, right? So
and that may play to their advantage, right? Because
yes.
they may have time and space in their mind to think
creatively.
Right?
Yeah.
So that's the big challenge. How do you give student a foundation without stifling their creativity?
Yeah, I think
that's very hard.
I think that's even a bigger challenge than the big data challenge.
Oh yeah, absolutely.
Yes, that's great. So kind of now, of course, we'll be talking about this system thinking and also the big challenge. Now, I'm really curious about you are now looking at this flapping wing Microair vehicle.
That was a lot of fun.
This seems really exciting. Can you tell us more about it?
Yeah, that was a lot of fun. It's a research that started. Well, it's concluded now. A couple of years ago, we started as a collaboration with the Air Force, actually. So I was there for a summer during a summer fellowship program, and they said, okay, we have this problem. We are trying to build vehicles that miniature vehicles that are capable of doing maneuvers that fixed wing vehicles are not capable. For instance, perching or very very rapid type of maneuvers, and we're looking at flapping wings. Okay, so but we have some understanding of the aerodynamics behind it, but we don't know how to design a flight controller for this sort of vehicles. And if you think about it, this is very different, right? Because the way thrust is generated is very unconventional. You don't have jets or anything of that sort. So very different dynamics, very different scales. Again, I know nothing about aerodynamics, but once I got a certain type of equations to work with, I immediately recognized that from the control perspective, this was fascinating because, well, the control input wasn't there. I mean, these things, you could control them, but what are the control parameters in the frequency of the flapping, the angle of the wings, the angle of attack? Something that required interesting mathematical manipulations that were not what I was accustomed to. So I had the chance to learn theory that I didn't know at the time, like averaging theory and sort of thing. And I became very interested. So we started this collaboration, and then we had a grant with another friend of mine from Ohio State University, Professor McNamara, who is not a control guy at all. He's an expert in structures. So we start looking at effects of wing flexibility on the controllability of this vehicle, because these wings the flapping wings are very very flexible, and this is a positive thing because you can produce more thrust, but it's also negative from the point of view of control because you have a lot of interactions that you need to take into account. So we had experimental results as well, and from my perspective, it was very interesting because apart from the little that I have learned on the aerodynamic side of things, because my knowledge is my understanding is very limited, but from the system theoretic side, how these different components integrate the mechanism, the linkages, the rigid body, the flexible dynamics, the aerodynamics, and the mathematical theory behind this was very, very fascinating. And I love the opportunity to learn techniques that then I used later, but I didn't know much about it. So it forced me to sit down and think of different methodologies.
That's very interesting. So
Yeah.
you said that this project kind of has concluded.
Mm-hmm.
So but I'm curious, thinking about, because it's kind of, for human beings, like, why did we make airplanes? Like, we wanted to mimic the bird,
Correct.
but of course airplane.
Don't look like
Yeah, airplane is not a big bird, right?
No,
They
not at all.
they have totally different.
Totally different.
So are you saying like this kind of flapping wing seems to be able to get us closer
Yes.
to the bird? But what's your general sense about the direction? Are we going to be able to make, like, for example, 80% bird-like, like kind of microair vehicles? Are we going to be able to make it?
Yes. I believe so. I strongly believe that. There are big challenges, which are technological challenges. One big challenge is how to power this vehicle. And because the payload that the flapping wing vehicle can carry is limited. And batteries have a substantial weight and a substantial payload. So that is one challenge, is how to have an affecting propulsion system in terms of battery and energy management. The second is, of course, related to sensors and how you can navigate the perception part of flying and autonomously a flapping wing. But we made a lot of progresses, well, not me personally, but the community made a lot of progress. There's the group of Professor Wood at MIT is doing fantastic work on really, really tiny flapping wing vehicles, but tiny. So it's amazing the way what technology is doing, and is in a sense a system person.
Great.
So we are very, very close to, I wouldn't say making this mainstream, but
that's I think really exciting to know.
Yeah.
Of course, I know, like, kind of we dreamed to fly, and we realized that dream, and that actually enabled our mobility, our travel tremendously, right? So kind of when all these kind of aviation system, including airplanes, they enabled our traveling, that gives us a lot of benefit, but we didn't realize that actually it has a lot of external impacts, including like noise pollution. I believe your talk is going to be about this. I know that we're running out of time and we need to go downstairs to get you ready for your talk, but I do want to mention that's why kind of your talk is going to be about how can we optimize and even compromise such that we can, while we are enjoying this kind of technology-enabled travel by airplane, we do want to reduce the impact to the community.
Noise control is something that again was prompted by this collaboration with the Air Force, and we looked at some interesting phenomena, and this was really my eye opener, right? Because I started working with people who had never heard about control and computational fluid dynamicists, experimental fluid dynamicists, and it took a while before we could come together. And well, of course, we had a project, we had an idea of what we wanted to do, but I didn't know whether it was possible to do it, and they didn't know that there was a way to do it besides just trying things out and see whether they worked. And eventually we were lucky to find a common ground, and we were very successful, I have to say, in that we were able to produce perhaps the first experimental results on closed loop control of cavity resonance, or one of the first, and it was very nice.
Great. I think this is really this is really a good place, a prologue to your Ezra system seminar, and I now we mentioned this in our video, so hopefully if people are interested in learning more about that aspect, we have also that video to be available publicly. So
thank you.
I think thank you so much, Andrea.
Thank you very much for the opportunity. It's a pleasure.
Yeah.
Thank you.